So here is an example for PES data for neon. If you look at this graph, you can see the relative number of electrons, and here you can see the binding energy. The binding energy is large on right side in this case. Normally it is from left to right, and we will consider here is the nucleus. So pay attention to the direction in which they have scaled the energy. Similarly, look at the peak height. These lines are also just for comparison. That doesn't mean each line represents one electron is added. This is just to compare the height of the peak and to get the proportion to the other peaks. So but for neon here, since it is 100, I will consider this one as I will interpret this peak is closer to nucleus. And this peak and this peak, we will consider this one is away from the nucleus. And by looking at that, we can see that this is taller and this is shorter. So two or second shell will have two orbitals we know, s orbital and p orbital. So the p orbital is taller and s orbital is shorter. So when you compare the heights now, the height of this peak is similar to this peak, same height. That is the reason they are giving the line. So since they are the same height and we assume that, or we interpreted this one as closer to nucleus, we can say that this is 1s2, this is 2s2. And now how can we see the proportion without using a ruler? We can just count the number of lines here. For s orbital, we saw 2 lines, and then we can see 3, 4, 5, 6. That means it is easy to find the proportion between these two peaks by looking at the line. So since it is 3 times taller than this one, and we interpreted this one as 1s2, this is 2s2, so that means 2 electrons, so it will be 3 times. So 2 times 3 will be 6 electrons in this peak. So that's how we are interpreting the PES data. So here you go. Energy to remove an electron is called binding energy here, and it is measured in electron volts sometimes, so watch out the unit. And the conversion is here. You don't have to memorize the conversion or anything. If there is anything to be converted or specific unit, they will mention in the x-axis. Now we will see for oxygen. So again, this is also in the reverse order, the energy is recorded. So since it is closer, and also look at the number of lines now, 1, 2, 3, 4. That doesn't mean it is 4 electron. It just means that this peak height is same as this peak height. And you can see the proportion here. So 1, 2, 3, 4, 5, 6, 7, 8. So this is just the double. So 1s2, 2s2. So double the electron means this is 2 electrons. So double the electron means 4. So 1s2, 2s2, 2p, 4. Now identify the element whose PES data is shown. Again, it is in the reverse order. So this is same height. So since it is more energy, we can say 1s2, 2s2. And how tall is this one compared to this one? 1, 2, 3, 4, 5, 6. So 3 times. So it will be 2p6. And this is half of this one. So it will be 3s1. So how many electron? 1, 6, 7, 7 plus 2, 9, 9 plus 2, 11. So this is going to be for atomic number 11, which is sodium. Now sketch the expected PES spectrum for aluminum. So look at the atomic number. Aluminum has 13 electrons. So how is it arranged? We already know 1s2, 2s2, 2p6, and then 3s2, 3p1. Okay, look at this height of this one, and also look at where is it moving. It is little away from the nucleus. The energy is not that much. So 1s2, 2s2, 2p6, 3s2, 3p1. Total how many electrons? 13 electrons. How to interpret for hydrogen versus helium? And now here the peak height is double. Let me see, 1 2 1 2 3 4. Yeah, it is double and it is single. So since it's saying hydrogen, we know hydrogen electron configuration is 1s1. Since already they said helium, we already know it is 1s2. So peak height double means it has double the number of electrons compared to hydrogen. And now look at the energy. Energy is decreasing this way, again opposite than the normal one. So energy decreases. For this one we need more energy, this one we need less energy to remove that electron. So what is that means is this one has more proton in the nucleus, so Coulombic attraction is higher, so it requires more energy to remove the electron compared to hydrogen. Hydrogen has only one proton in the nucleus, so less Coulombic attraction, so it is easy to remove the electron from the valence shell. That is why the peak for the 1s is little away from the nucleus or less energy from here when you compare, and this one need more energy to remove the electron. That is why it is closer to the nucleus it is showing. That is how we are interpreting. Here is the answer. How to compare nitrogen and oxygen? So when you look at the graphs here or the peaks here shown here, but since they said nitrogen and oxygen, we can compare from the periodic table. Oxygen has how many electron? 8 electron. So atomic number is 8. That is nuclear charge is going to be, proton number is going to be 8. And nitrogen has 7 electrons. So that means 7 protons in the nucleus. So the nuclear charge means in the nucleus there are 7 protons. So who will pull the electron closer? Who has more nuclear charge? For oxygen, because 8 protons. So it will be closer to the nucleus and it need more energy to remove the electron. This one less energy is required and the peak height looks the same. So because they already mentioned that it is from the 1s electron. So why is the peak for nitrogen farther to the left? Because less nuclear charge, so less pull towards the nucleus, Coulombic attraction is less compared to oxygen. You cannot say less just without comparing anything. So compared to oxygen, it is less. So it needs less energy. So that is the reason the peak is further to the left.